The world is constantly changing. Technology continues to develop, especially medical technology. Researchers are constantly innovating to ensure the highest quality of health for humans. Among recent technologies, CT scan has transformed into a very useful imaging modality. Images produced by CT are able to provide an accurate detailed look at the patient's organs in a short time, supporting accurate diagnosis. Image quality is a vital aspect that must be achieved in CT examinations. Research on CT scans continues to grow rapidly. Researchers continuously innovate to give their best contribution to society. All efforts are made to improve the effectiveness of the health services. One of the results of this innovative research is IndoQCT. IndoQCT is a software to automatically evaluate the quality of CT image. IndoQCT can be downloaded on the website www.IndoQCT.com. IndoQCT is able to measure various image parameters from a variety of phantoms available on the market. Measurements with IndoQCT are carried out quickly and accurately. With only a click, the calculation is carried out automatically without much intervention from the user. IndoQCT has three main objectives. First, it's a tool for medical physicists to effectively and quickly accomplish their task in routine quality control of CT. Second, it's a scientific tool for CT scan research. And third, IndoQCT is a tool for educational purposes, especially education regarding the quality of CT images. Unlike previously available software which were limited to certain parameters and phantoms, IndoQCT is capable of measuring various parameters from a variety of available phantoms, such as the AAPM CT performance phantom, the ACR CT accreditation phantom, the CAPFAN phantom, the GE CTQF phantom, the Canon TOS phantom, the Philips CTQF phantom, the Siemens CT phantom, the Newsoft CT phantom, and the anthropomorphic phantom. IndoQCT can also generate synthetic images using a computational approach called the computational phantom, which is useful for educational purposes. The main capabilities of IndoQCT are to measure CT number, noise, spatial resolution, slice thickness, low contrast detectability, alignment, gantry tilt, distance, and distance between slices. IndoQCT is also reliable in measuring image quality metrics directly from patient images. It's advantageous for simplifying and increasing the objectivity of the dose optimization process. IndoQCT is also equipped with several additional features, including texture analysis, some noise reduction, several windowing options, including multiple windows blending in the form of red, green, blue images. And image reformatting Osman sagittal, coronal, oblique, and irregular planes. IndoQCT will be able to connect the picture archiving and communication systems to facilitate user in collecting images directly from DICOM servers. It doesn't stop there. With IndoQCT, you can store, measure data to an integrated database. This storage has been facilitated with an export tool to save data in Microsoft Excel document format. IndoQCT provides convenience in the aspect of efficiency, measurement objectivity, universality, and portability. Many international publications have been produced using this software. Research opportunities with IndoQCT are ongoing so that the number of research projects using IndoQCT will continue to rise.
Well, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Welcome back to the second session of the online summer course in Medical Physics 2025. And this afternoon, we will have the lecture from University Science Malaysia with Associate Professor Dr. Nurdiana Osman and team. We will have a lecture about the spatial resolution, including the visual observation, MTF, and also TTF. Associate Professor Dr. Nurdiana Osman, as our speaker for this session, is a lecturer and also a researcher from the University Science Malaysia with the expert in the field of CT imaging, computed tomography, diagnostic radiology, medical imaging, physics, and also medical image analysis. Maybe we can greet Dr. Associate Professor Dr. Nordiana. Hello, Prof.
Hi, Suchi, can you hear me?
Yes, but your volume, maybe you can raise up your volume.
Okay, sorry. Can you hear now?
Yes, we can hear you now. Okay, how are you, Dr. Nordiana?
Alhamdulillah, thank you. I'm great.
Alhamdulillah, we are very happy to welcoming you in this event. Thank you for joining us. And how about the weather in Malaysia?
Oh, okay. So it's raining this morning, but
Hmm.
okay.
Okay. Okay, we are really want to know about the spatial resolution. So without any further ado, so please to Associate Professor Dr. Nordiana to present your material. The stage is yours, please.
Okay, thank you, Suchi.
Thank you.
Okay, can we see my slide?
Yes, we can see it now.
Okay. All right. Assalamualaikum and a very good afternoon to everyone. Okay, so I'm Dr. Diana from University Science Malaysia. To be exact, I'm based in Advanced Medical and Dental Institute, which is IPPT in Penang. So I would like to thank the organizer, especially Dr. Anam and team, for inviting me again to be the speakers for today's session. Okay, so today I will talk about spatial resolution and then the parameters that we use to determine the spatial resolution and how the measurement is performed. And then I will also share my experience using IndoQCT. So I didn't bring my teams, but Dr. Anna will also help me during the demonstration. So, okay, I'm first joining the summer course, I think back in 2023, I think, as a participant. And then I found out that IndoQCT is very attractive and very useful for quality assurance measurement. So, and then we implement and try on our daily routine QA, and it's a very useful. And then starting last year, I joined as a speaker with my team, and we also sharing our experience. And this year, again, as invited speaker. So actually, we have a few collaboration with Dr. Anam, and we also have joint publication with Undip. So hopefully in the future we can have a more. Okay, so I also have a few students that employ IndoQCT and in their research work. Okay, so maybe I can share with you today. Okay, so without further ado, I will start my talk. Okay. So this is the guideline, the content of my talk today. Okay, so for spatial resolution, I think it has been introduced early by Prof. Can't remember the name. Okay, in image quality. So we know in general, image quality has a few parameters, and one of them is spatial resolution. Okay, we have contrast resolution, we have a noise, and also artifact. Okay, for this morning session, Dr. Anam already covered noise and how we would calculate NPS. Okay, so now is spatial resolution. Okay, so spatial resolution is actually in some textbook they refer to high contrast or detailed resolution. is actually defined as the ability of the CT imaging to resolve between two closely adjacent objects from each other. So how the system resolve between two small objects. Okay, so spatial resolution is used to describe visible sharpness of fine borders, okay, or edge of the structure. Okay, and then usually determined using point spread function, line spread function, MTF, modulation transfer function, and also ERF. Okay. Okay, so usually we will use line pair phantom to assess our spatial resolution of the system, of the CT imaging system. And usually the spatial resolution is measured in line pair per centimeter or line pair per millimeter. It depends on the system. Okay, so this is a line pair in CAD fan. So usually we will calculate how the system can resolve. Okay. Yeah, a perfect imaging actually will give you just a point. If you have a small object, the best CT imaging should give you a sharp point. But usually because of other factors that affect the point spread function, then you will see a blurry edge of the point. Okay, so you will get like a curve here. It's not a perfect point. So it is called as a PSF or point spread function. Okay, and this is made due to our CT image reconstruction, FDP or iterative that we use. And then the type of filter is either your acquisition filter or reconstruction filter, okay, which is your kernel. And then we also have the source or the beam, okay, which also depends on the focal spot size. Okay, and then it can also be affected by collimation of the system. Okay, and then the size of detector, we know we have nowadays is MDCT, multi-detector CT, and different system will have a different size of detector depending on what we have. Okay, so it also affect our point spread function and also detector efficiency, how it convert the photons to light, and either the efficiency of the detector to convert the X-ray photon to signals. Okay, these also the factors that affecting our point spread function. So the ideal system should give you a sharp edge and a point without the spread of the signals. But in reality, we can't have an ideal or a perfect point each. Okay, so that there will be a spread. Okay, and then we know that most of the CT system use scintillator. We still use scintillator detector. So the scintillator detector, the function is it will convert X-ray photon to light first, and then it will convert to digital signal. So the spread of light also affect our point point source or point object. Okay, so there will be a spread of the signals. Okay, so the edge of the object that we detect actually determine our spatial resolution. Okay, So it's actually a measure of the ability to differentiate small objects. Okay, for example, if we have two small object that is with a small gap and it is very near to each other, this a good system should separate and able to display these two objects as a separate object. But in certain system, when that factors affect, so you may see it as a one object. Okay, so the gap between these two objects is very small, and then it can't be differentiated. Okay, so if the system has a good spatial resolution, it can able to visualize the system as two separate objects. So that's the sharpness of the image. Okay, so this is what we see in spatial resolution. Okay, for example, these two image, okay, has different spatial resolution. So which do you think that have a better spatial resolution? Okay, so a good system should be able to differentiate the line pair at the smallest possible. Okay, so here on the left, okay, you can see up to 4 objects, but here you can only see for 2 groups. Okay, so in here, this system has a better spatial resolution because it can give better resolution, or you can see more line pair compared to here. Okay, so here the first group you can see clearly. And then here, okay, this is on clinical image. So the left image give you better spatial resolution, but here you can see it is a smooth, but you can see the edge very well. Okay, so you can see that this system has a better spatial resolution. Okay, so in clinical application, the spatial resolution is important, especially for high resolution CT, because high resolution CT usually we use in lung or thorax chest CT. So because we want to see the disease of interstitial lung disease. Okay, so usually for HRCT to enhance the spatial resolution, we should use a thin section or thin slice. Okay, usually in the range of 0.6 to 2 mm. And then we also use a sharp kernel, okay, sharp reconstruction algorithm, which is also known as high frequency algorithm, okay, to enhance the spatial resolution. Okay, so HRCT in clinical application is actually the aim is to detect and characterize the extent of disease affecting pulmonary parenchyma and also airways. Okay, so for this one, it is superior to chest radiography for detection of lung disease. Okay, so HRCT is usually used in chest or thorax. Okay. And then we also have nowadays ultra high resolution for more advanced CT, modern technology. So for ultra high resolution, it's actually the detector is small, smaller than the conventional one. Okay, and it's been used to see the extremities and then calculi. Okay, so this is one of the example, the use of ultra high resolution. Okay, the advancement is by using smaller detector size. So you actually can improve the resolution of the image. Okay, and then this is the evolution of spatial resolution. Now we have photon counting CT that been covered by I think Prof. Yeong in the first lecture. So it's actually the new technologies. Okay, because photon counting, we didn't use a scintillator detector. So actually, in photon counting CT, the spread of light is avoid because we eliminate the conversion of photons to light because it is directly convert X-ray to signal, digital signal. So the spread of light is excluded. So in terms of spatial resolution, it is more improved. It can be improved using photon counting. So as you can see here, the spatial resolution is improved using photon counting. Okay, so now we go to methods that been used for spatial resolution measurement. Okay, so usually in our daily practice, we just assess the spatial resolution using visual observation. Okay, this is the common method that we use for our routine quality assurance at hospitals. Okay, so usually physicists only test and then they just count how many line pair that can be seen. So that is visual observation. But actually using visual is a very subjective and there will be a variation among observers and also it is limited. You can see beyond your eyes. So usually we use other techniques to also assess the spatial resolution. For example, we use MTF, okay, by using point spread function or age spread function, okay, PSF or LSF. And then we also use TPF, okay. So I will go into detail each parameters. Okay, so this is the common method that you've been used to assess the spatial resolution in CT. Okay, so visual assessment usually just a simple method. We just scan and then we visualize the image of the phantom. Okay, for routine QE. And then we just characterize how many line pair that we can see from the image. Okay, so we just measure the high contrast line pair or whole pair object, okay, depending on your phantom. So from my experience, before I was introduced to IndoQCT, I do visual observation. Okay, we just count how many we can see and then we just calculate or measure the gap between the line and then we just report. So that's the most simple technique. Okay. So I believe most of the physicists use this method for spatial resolution. Okay, so we have a lot of phantoms that we use to assess the spatial resolution depending on your CT scanner at your center. Okay, for our center, we use CAT fan. Okay, that's the common. And then we also have AAPN CT performance, and then we also have ACR. Okay, for spatial resolution, we have line pair, and then we also have GE phantom. So this is the variety of phantoms that we use to assess spatial resolution. Okay, you see. Okay, so usually in visual assessment, you can only see how many line pair that you can see. Okay, and it should be clearly resolved, the line pair. Okay, so for objective assessment or visual assessment, you just count how many that you can see. Okay, for example, you count the groups, okay, that clearly resolve. Okay, so if you see one group, the first gap is clear, but the second gap is not really clear. So usually we didn't count that. We should count only the line pair that is clearly resolved. Okay, that's the visual assessment. Okay. This is for the phantom that use line pair. And then we also have another types of phantom that use whole pair pattern. So we calculate the distance between each pole. So this is for AAPM phantom. It use a full diameter. Okay. So you have to see the gap that clearly resolved. Okay, for example, like this, it's already not, you can't see the gap, so you can count it as the line of hole that you can see. Okay, so we just count and take into account only the hole that is clearly resolved. Okay, same as line pair. Okay, so for limiting resolution for CP is commonly between 0.5 to 2 line pair per mm. Okay, and then typical limiting for screen film is 4 to 20 line pair per mm. Okay. Okay, this is showing that CP has better spatial resolution compared to screen film. Okay, because the line pair that you can see is more smaller line pair. Okay. So for visual observation, actually the advantage is it easy to be performed. Okay, and anyone can just assess. Okay, but disadvantage is as I mentioned just now, it may be biased for observer between observer because different observer has a subjective assessment, so it will be varies among observers. Okay, and then it also depends on expertise of observers. Okay, for example, in Malaysia, usually for annual QA, it is performed by Class A or certified medical physicists. So usually they have more experience on observation compared to physicists on site. We sometimes didn't do. We maybe do it monthly or maybe in 2 months, once in 2 months or once in 3 months, depending on the availability of the physicists. Okay, because it's not compulsory, but the requirement is once a year. Okay, annual QA. So the expert is the Class H, which is those certified medical physicists. Okay, I from my experience, usually I try to compare my observation and them. Actually, they are more they can see more line pair compared to me. So it also depends on the expertise actually of the observer. And I also test on with my student, which is a lesser experience. So they actually can see less line pair. So as I said, the limitation is it depends also on the observers. Okay? And then it also depends on the correct window that you use. Okay, so usually the recommended window, CT window for spatial resolution is a sharp kernel or sharp windows, the bone windows. Okay, and then it also depends on other protocols. For example, the slice thickness that you use during the phantom scanning, and then the kernel that you use during the scanning. It also play an important role in your assessment. Okay, so you have to choose the optimum protocol so that the spatial resolution assessment is optimum. Okay, so there's other other parameters that affect the subjective assessment. Okay, next method that we usually use is modulation method, but for this one, you need a certain software to calculate. Okay, if you use manual, it's quite tedious. Okay, so for modulation method, actually, we calculate the line pair and then the contrast, okay, between the line pair and the gap, okay, and then we modulate to become a curve for MTF. Okay, so this is the input and this is the output image. Okay. Okay, so a good image or a good line pair that is clearly resolved will give you a good contrast, but for the line pair that is not clearly resolved, it will give you lower contrast. Okay, for example, like this, you can clearly see the gap between the line, so it will give you lesser contrast. So this is how the modulation is performed. Okay. And then between the line pair, it will be transferred, modulate, and then it will be plotted as a MTF graph or spatial frequency. It is a cycle per mm. Okay, so it's actually the measure change in the amplitude of the signal. Okay. Okay, so the practical method is actually first introduced by Ronan in 1982. What they do is they measure it manually and then they transfer it as a MTF. Okay, so first performed by in 1982. Okay, so this is how they calculate the MTF. Okay, the modulation. Okay, and then this is how the curve of the MTF is plotted. Right. And then the MTF, we have point and also age modulation. Okay, for the point spread function of PSF. Okay, so usually we measure the point, okay, on the phantoms, and then we plot the intensity, and you can see the 2D point spread function. Okay, it is actually the spread of the age of this small object. Okay, so that's the intensity. Okay, and then from this, we modulate and normalize, and then we plotted the MTF, the spatial frequency. Okay, this is a study by Dr. Anam and team in 2019, how the PSF is converted into the MTF. So MTF actually, the curve is actually, the x-axis is a spatial frequency, and then we calculate the line path. Okay, this is also study done by Dr. Anam and team. Okay, so they measure the 50% and 10% frequency, which is determined from the curve. And then MTF 10% is actually the limit of visual observation. Okay, beyond this, you can't see or you can't differentiate the line path. So that's the MTF 10%. Okay, so this is for 50%. Also reduce. Right. Okay. So MTF 50 is actually the MTF value at 50% here, and then this is for 10%. Okay. So it is a common metric that we derive from MTF. So they actually represent the spatial frequency at 50% MTF. Okay, so it is often used to measure the resolution, which indicating that the contrast is reduced to half of its ideal value. Okay, the ideal value is 1, and then MTF 50 is the contrast is 50%. Okay, and then this is also study, a previous study. This show the in-plane spatial resolution of MTF. Okay, this is using the standard kernel, but this is using the bone kernel. Okay, if we that's the curve. Okay. So we have different phantoms to measure the points spread function, PSF. Okay, so for CAD-FAN, usually we have 1 point here, and then this is for ACR, and then this is for AAPM. Okay, so this is for point spread function. So this one, depending on your system phantom, which one will you have? Okay. Okay, this is for Nyquist frequency. You can also use it to represent your spatial resolution. Okay, it's actually, this is the equation. Okay, Nyquist frequency, the measured spatial resolution should be lower than Nyquist frequency. Okay. Okay, Nyquist frequency is actually the limit frequency that can be seen by the system. Okay. Okay, and it also depends on the FOV. Okay, so for smaller FOV, the Nyquist system will be higher compared to larger FOV. So a small FOV is actually better for measuring spatial resolution. Okay, for example, this is smaller FOV, which only focus on the point to give you better spatial resolution. All right, now I go to each MTF. Okay, for example, just now, for point spread function, we just take 1 point. Okay, and then we see the spread of that point. Okay, and then it can also give you the line spread function. Okay, for each response, it's actually between two structures that has different contrast, and then we measure how good the resolution between the edge. Okay, for example, you can see this one. Okay, so a sharp edge will give you straight line between these two points. Okay, these two contrast, okay, between dark area and bright area. Okay, the ideal system with a good spatial resolution, but in reality you can't get a straight line. It will be a spread of the edge. Okay, there will be a blurry spot also. Okay, because of the that parameter that I explained before. Okay, so this is how we plotted the curve of the edge response. Okay. So this is the ESF. Okay, this is the study done by Doge in 2016. So they studied the MTF. Okay. And then, yeah. So LSF, we can also obtain line spread function from edge spread function. So it is obtained directly from the image. Yeah? And it can also be obtained if you don't have the line spread function object, so you can get it from the SFF. Okay. So this is how the plot using delta ratio. This is a study by Dr. Anam and team in 2018. So the automated modulation transfer, okay, to obtain the ESF and also line spread function from the ESF. Okay, this is another study to get the MTF curve for different filter. So this is a different filter using FC13, FC30, and also 52. And this is the comparison of MTF using different FOV. Okay, the limitation of the MTF, for example, if you use this phantom, it should be rotated. Okay, so because it cannot be directly used for MTF correction because inhomogeneity in this part, because we have CTDI, we know it has a hole, okay, for ion chamber measurement, so we need to rotate the phantoms to avoid this inhomogeneity. So the automated measurement will rotate the phantom first. Okay, and then this is for tail replacement in 2019, studied by Dr. Anam also with the tail. So what they do is they replace, okay, the tail so that it become flatter. Okay, so you get a perfect EFF. Okay, so this is the result of tail replacement. Okay, homogeneous phantom and non-homogeneous phantom. We show a good MTF. Okay, so using automated measurement for each MTF, it gives you the orthogonal lines of the edge. Okay, so it measures from the edge of the phantoms. Okay, I will show you later using IndoQCT, and then during the demonstration also, Dr. Anna will show you also the edge MTF. Okay, so actually the rebinding is used, okay, because to get the because we want to measure MTF with standard FOB. So the IndoQCT has the rebinding method, okay, for MTF. So now I go to PTF, okay, task transfer function. Okay, so for example, when the imaging system is known to behave non-linearity, so MTF may not represent the imaging system response. Okay, so in this scenario, the system resolution depend on the object contrast and also background noise level. So MTF will be the good parameter to represent your spatial resolution. So you need a task-specific matrix known as task transfer function or TTF. Okay. So TTF actually the measured same as MTF, but it takes into account the object contrast and object radial location. Okay, beside that, it also take into account the background noise. Okay. Okay, for example, okay, you have one object, okay, and then it will take into account the background noise and contrast. Okay, in comparison with the ROI. Okay. So for example, here for the ethylene, okay, so it will calculate the H spread function, and then it will convert into the LSF, line spread function. And then from here, you will get the MTF measurement, okay, based on the PTF task function. Okay. All right. So the H spread function you can calculate at the x-axis, or you can also calculate at the z-axis. Okay, z direction resolution. Okay, this is for z-axis. Okay, this is for x-axis. Okay, and then this is based on the AAPM report. So we extract the H profile, and then we convert it based on PTF, and we will get a better, a more meaningful MTF. Okay, for example, here you have this phantom, okay, with different insert, okay, or different object. You have air, poly, and then you have acrylic and also bone. Okay, so it will calculate, it will include the contrast between these two objects, okay, this object and also background, and then it will plot to view the MTF. Okay, so as you can see here, the spread function, okay, for different inserts. Right. So that's the PTF. Okay, so now I will show you how the IndoQCT can measure for you, automatically measure for you the spatial resolution. Okay. All right, so in routine QA, usually you will use any phantoms, commercial phantom that you has in your center, and then you will scan using recommended protocol, and then you will visualize, okay, the phantoms. Okay, so usually it is known as a high contrast resolution test, HCR test. Okay, for example, here it is a CAT fan. Okay, so in my center, we usually use CAT fan for our routine QA. So we have 600. Okay, so the positioning of the phantom also play an important role also. Okay, if you didn't properly position your phantoms, okay, you won't get a good image, and it will affect your assessment. Okay, because usually for HCR measurement, it is recommended to use as thin, the slice thickness as thin as possible. So usually we will use 1 mm slice thickness. So the 1 mm slice thickness should be perfectly on the on this on these features. If not, you won't get it will be cut away, and then you can get a perfect line pair. Okay, so this is based on my experience. Sometimes we steal the phantoms, and then you can get to see or to observe all the line pair on the same thickness. Okay, so you should properly position your phantom. That's the first step for the measurement. Okay, so it depends on the expertise of the physicist. Okay. So usually for CAT fan, there will be a box, and you can put it on the box, and you have to carefully measure so that it is correctly on the laser light. Okay. Okay, in Malaysia, the guideline, okay, for the standard, the acceptable limit is based on what is provided by our Ministry of Health. Okay, so the performance standard is more than 5 line pair per centimeter. Okay, so you should have seen more than 5 line pair. Okay. So, and then if you are using CAT fan, usually in the manual, it will provide you the gap size as reference. Okay, so it has 21 line pair, and then you have to measure how many that you can see. Okay, so at my center, usually we do monthly QA tests, and one of the image quality testing is for high contrast resolution. So this is the common report that I usually report for monthly QA test. So this is the recommended exposure factors given by the vendor. Yeah, so you have to refer the manufacturer recommended protocol for your QA test. Okay, and then usually I just use the simple method is by using a visual observation. Okay, so I should count how many that I can see, okay, visually. Okay, so from my experience, at my center we have CT Siemens somatum definition AS plus. So usually for spatial resolution we can see up to 9 pair. That's the maximum that we can see. Okay, but in certain month I can see 8, maybe because yeah, some technical issues, so I can't see the 9. Okay, but in our routine is like 9 pair that I can see. So and then in our monthly test, we just report what is the measured gap size that we can see, and then we compare with the reference gap size. That's the simple reporting lah. We just report using visual observation. Okay, so I will just measure the gap between the size, the line pair, and then we take the average. Okay, so because the acceptable level by the Ministry of Health is more than 5 line pairs, so it is passed, okay, for our system. Okay, so this is the routine report that I did at my center. Okay. Using IndoQCT, actually, there's other standard that is provided by IndoQCT. So I think in Indonesia, they use Babetan standard. And then there's also AAPM, IEE, and SCR standard also. And then you can also custom based on your country requirement. Okay, so this is for the monthly PE. Okay. So I never try the custom because maybe in future I can ask Dr. Anam, but usually because I did it manually, so I just compare with the standard regulation by my country. Okay, and then I also added other parameters using IndoQCT. Okay, because I found out that this measurement is usually limited. So I try IndoQCT for my routine to explore more on the spatial resolution. Okay. All right, this is the regulatory requirement in my country. It is provided by Ministry of Health. Okay, so I believe other country has their own regulation, similar with Indonesia also, which is Babetan. So just sharing from Malaysia. Okay. All right. So that one is just a simple measurement using visual observation. Okay, and then for automated measurement, where you can explore more parameters, you can use IndoQCT. So I found it is very helpful from my experience because my conventional method, I just use visual observation, which is limited. So since we are collaborating with Dr. Anam, so I use also IndoQCT in my routine test to check and compare the manual measurement with the automated. Okay, so I believe this one everyone has download and installed in your PC. Okay, so this is the old version. I think the new version is you have more features. Okay, so I show you the version 24 version. Okay, so it has for spatial resolution. You can go to this. Okay, when you open IndoQCT and then you read your image. Okay, you can use your own phantom image or you can use the sample from the IndoQCT. It has a variety of phantoms, so you can test and try. Okay, so this is all the parameters that offered in the IndoQCT where you can use. Okay, it also gives you a visual observation, and then you can also calculate point MTF, H MTF, and then Z MTF if you are calculating at that direction. And then you also have PTF. Okay, so this is for visual observation. Okay, it will draw automatically the ROI on the line pair. Okay. So you don't have to manually calculate. Okay. All right, and then it will give you how many object number that can be seen clearly. Okay, and then it will give you the size of line, okay, per mm, and then this is the line, the spatial frequency. Okay. So for this image, it is passed using the standard Tempatan Indonesia standard. So the system is fast. Okay, so you can try using your own phantoms later. So you see either your system is fast or not. Okay. This is another phantom using cat fan. Okay. So object since is 6, and then okay, this is using AAPM. And then next parameters or next metric is point MTF. You can also measure. So usually it will automatically detect the point. Okay, and then it will measure for you the it will give you the parameters of matrix frequency, MTF 50, and also 10. Okay. Okay, this is for cat fan. And then this is for point MTF. So it will give you the graph of the MTF, PSM. Sorry, it will give you the position. Okay, for each MTF, so same as PSM, it will give you this value. Okay, and then it will draw on the each of the phantoms. And then it will also give you the graph of PSM automatically calculated for you. Okay. So this is using cat fan. This is from my phantoms. Okay, for my TE phantoms. Okay, monthly TE. So this is the EFF that is wrong. Okay, because usually for MTF, I didn't calculate for Z direction, because usually we just take the axial image and then we just take one slice. So I didn't calculate for Z MTF. But I believe later during the demonstration by Dr. Anna, maybe Dr. Anna will show us the exact MTF. So, and then for TTAF, it takes into account, as I mentioned just now, the contrast between the region and the background. So usually we will use these phantoms. Okay, because it consists of different insert, okay, having different contrast with the background. Okay, so we calculate the TTF. This one is phantom. Okay, this is using cat fan phantoms 600. Okay, so it will throw to you. Okay, and then it will give you the value of TTF 50 and 10%. Okay, for different insert. Okay, and then it will calculate for you the TTF curve. Okay, as you can see here, different insert give you different curve. Okay, the lowest is the acrylic. Okay, because acrylic has lowest contrast with the background. Okay, and then the highest is Teflon. Okay, so because Teflon is high density material, it gives you the highest contrast with the background. Okay, so it has a higher curve, okay, compared to acrylic. Okay, so this is the Nyquist frequency, okay, the limit of this our spatial resolution. Okay, and then 50% here, and then 10% here. Okay, so this is 50%. Okay, this is our recent study published this year. Actually, it is a work done by my PhD student, and this is a joint publication with Dr. Anam and in my field. We explore IndoQCT, and then we compare different iterative reconstruction methods. Okay, and then this study actually we want to compare 3 different iterative, and we want to see the effects of iterative on low dose CT. So we compare actually standard protocol, standard dose CT, and also low dose CT. In combination with iterative. So we test on different image quality and parameters, and one of them is on spatial resolution. Okay, this study is done in the data collection is done in Palestine, in West Bank, because my student is in Palestine. Okay, so we test on different CT scanner. We have Siemens, we have GE, and we have Philips. And each CT scanner has different iterative algorithm. So we test, and then beside the iterative, we also combine with post-processing technique. For example, here we use IDHC algorithm, which is for bone hardening correction algorithm. Okay, and then we compare between standard FDP and also iterative. Okay, so the measurement is performed using, the analysis of the spatial resolution is performed using IndoQCT. Okay, so this is for Siemens scanner, and this is for GE. But for Philips, different algorithm didn't give a significant comparison. Significant difference. Okay, so I didn't show here. Okay, so for this one, as you can see, actually iterative didn't affect the MTF, but only the IDHC has a significant difference as it improve the MTF curve. Okay. So FDP in combination with IDHC and iterative suffice for actually in combination with IDHC actually show improvement in MTF curve. Okay, and then for this one, actually in low dose, okay, it give in better MTF curve. Okay, but using standard dose CT, it has a lower HMTF. Okay. All right. So that's one of the study that we use MTF. We use IndoQCT for our research work in spatial resolution. And then we also explore for another parameters, for example, MPS, SNR. Okay. So that's the measurement of the MTF, automated measurement of MTF using IndoQCT. So the conclusion, okay, this is the final part of my talk. Okay. So we know spatial resolution actually is a measure of the ability to differentiate a small object in an image. So spatial resolution is actually representing the sharpness of the image. Okay, because in CT, for certain clinical indication, the sharpness is important. For example, in HRCT, and also in small structure studies. Okay, so usually spatial resolution can be measured using line pair or whole pair phantoms, depending on the commercial phantom that you have in your center. Okay, and then the metrics that we use is PSF, LSF, or ESF. Okay, so it is all the modulation transfer function. Okay, and for certain cases where you have non-linear imaging system, this metric may be not the ideal metric to represent your spatial resolution. So you have to use PTF. Okay. Actually, IndoQCT is one of the best tool, I think, for the automated spatial resolution, because it actually saves your time, and then it offers various metrics that you can explore to assess your spatial resolution. Okay, so from my experience, I think IndoQCT is best, okay, for our routine QA at the hospital and also for research work. So I think it's the best tools lah so far that I'm using. Okay, so I think with that, I would like to thank everyone for your kind attention. Okay, maybe I will pass to Dr. Anna for demonstration. Okay, I'm sorry because I'm using my laptop, so I didn't have the new version of IndoQCT on my laptop because I install it in hospital computer. So I think I will pass it to Dr. Anand. Thank you, everyone.
Okay, thank you, Dr. Nordiana. Maybe we can continue to the practice session with Dr. Khairul Anam. Okay. I'm sorry, Dr. Khairul Anam, we cannot hear your voice. Okay, for the question in the chat box, we will discuss it later. Waalaikumsalam warahmatullahi wabarakatuh.
That's yeah, thank you, Dr. Diana, for very nice presentation. And now I will demonstrate using IndoQCT for measuring spatial resolution. Okay, I will share my screen. Okay, this is our IndoQCT. And now I will demonstrate for measuring the spatial resolution on the RCR phantom. ACR phantom, this one. Okay, this is ACR phantom. And then to calculate the spatial resolution, we use the tab number 4. 1, 2, 3, 4. And there are 5 sub tab: visual, point MTF, HMTF, ZMTF, and TTF. This is for the latest version. Okay, and now we will try to measure visually. So to measure the spatial resolution visually, we can use the automatic one and manual one. Manual one meaning that we are the observer and decide what is the uh, minimum resolvable line per object like this. Okay, and now we will try. For example, this is the example, and then we can enlarge this. So to measure the spatial resolution, we should use this kind of the module. Okay, and then we move our slice to this one. So for manual visual observation, we should use the optimum window setting. And the IndoQCT give you two optional windows. You can use this one, the boon window, or this custom window. This custom window is based on the ACR with the window width 100 and window level uh, around 1100. Okay, this one. This is automatic suggestion for the IndoQCT for the window width and window level. And now for the manual one, you can count and see what the group of the line pair can be separated. This one I think can be separated. This one can be separated. This one maybe can be separated. And this one can also be separated. I think it is the minimum, the maximum resolvable line pair. So in this example, we choose the number 4. 1, 2, 3, 4. 4 and then calculate. So the size of line is 0.7 and the line pair is the 0.7. So compared to the IEA standard, which is 0.5, so our result is pass like this. This is for the visual observation. And this result is, as already mentioned by Dr. Diana, depend on our subjectivity. And now we move to the automatic one. The automatic one using the modulation method. And the equation are already discussed by Dr. Diana. And then we just click this button. And the IndoQCT will search like this. And this 1, 2, 3. So number 3. This is based on the using the equation already mentioned by Dr. Diana. Okay, and this is our ROI automatically located by the IndoQCT. Okay, like this, and this is our result. The object number is number 3, and the size of line is 0.8, and our result compared to the standard is pass. This is for the visual observation. And now we move to the point MTF. Okay, to measure the spatial resolution using point MTF, we can click this button, this tab, point MTF, and then we will see the example, enlarge. So we use this type of the module. There is two point here, and now and we will change the window to the standard one, soft tissue, for example, and then we change the slice to this one, We can see here there are 2 points, and for measuring the point, So we can choose the automatic one, or you can choose the manual one. If you choose the manual one, so you have the ROI, and you click ROI, and then you locate the ROI to this position like this. And you can measure, you can set the ROI size, and you can also make the option about the direction. Z-axis, meaning you measure the spatial resolution in the Z-axis, or X-axis, or polar coordinate, meaning radially. In this example, I will use the Y-axis like this. So meaning we measure the spatial resolution from bottom to the top position. And then we can also measure using the single slice or multi-slice. Okay, I set the parameters like this, and then I just calculate. This is the result. And the IndoQCT have two curve, the PSF, point spread function, and the MTF. And you can see here that there is so many noise here. So it is recommended for measuring the MTF by using the point object. You should use a very high dose, so your noise is very small. It is the standard dose, so the image is noisy. Okay, and this one is the MTF 80, and this one is the MTF 10%, and we have the result. This one, the MTF 10 is the 0.5. Compared to the standard, it is also fast. Okay. And now we will move to the using the Edge MTF. Edge MTF. In the Edge MTF, this is the example. So the Edge MTF will detect the edge function, the edge of the material. And this exam for the, you can choose the automatic one or manual one. For the automatic, we have many options. For example, you can use perpendicular or square or radial. This example, will have a profile perpendicular to the edge of the phantom. And algorithm using the gradient, you can choose maybe another algorithm using the distance transform, and the default is the gradient. And you can set the height of the line, in this example 16 pixel, and you can set the angle. The default is 90 degree. You can set up to 180 degree, and the right step you can step 1 or maybe 2, 3, and using the ESF shifting. It is, I think, the new algorithm. Maybe after this I will show you what is the algorithm for the ESF shifting, and you can also use the fitting and another option. Okay, now it is the standard one, and then I calculate. So the software, the IndoQCT, will detect the edge of this phantom. I will enlarge this phantom, and you can also zoom in. You can see this profile. So many line profile here, and then we make the profile, and then we calculate the average. After this, you will have the ESF, edge spread function. This one, this one is the edge spread function. This is the average from the many profile across the edge of the phantom, and then the IndoQCT will differentiate from the ESF to the PSF, point spread function, like this. And after this, the IndoQCT will do Fourier transformation to get the MTF like this. This is the MTF, and also the MTF 50 and MTF 10 will be calculated, and the result is displayed here. We have the result like this, and in my opinion, using XMTF, using this method is better and more resistant to the noise. So you can scan the phantom with the standard protocol. But if you want to measure using the point MTF, you should use the very high dose because the method is very prone to the noise. Okay. And now we move to the another method. I close this one. Okay. And then you can change this one from 90 degree. Maybe I set to the 180 like this. So the line will be half of the phantom. You calculate. This is the result. The result like this. Okay, and I think it is better because many data are used for the measuring the MTF. Okay, this is the MTF, this is the PSF, and it is the ESF. Okay, like this. And now we move to the TTF. TTS is task transfer function, and it is, I think, the latest metric for measuring the spatial resolution. And the TTF is a good metric, especially for the iterative reconstruction, because as already mentioned by Dr. Diana, in the iterative reconstruction, the image is behave non-linearity, meaning that the spatial resolution is depend on the contrast, depend on the position. Okay, so I think the TTF is much more better compared to the standard ESF or PSF. Okay, and I click this one, TTF, and then this is the example. So we use the phantom, which is already usually used for the city number linearity. Okay, and then we move to the this one. This one is the image for the measuring city number linearity, and of course, as usual, you can measure automatically or manually. You can use the ASF shifting. You can use the fitting method. You can measure on the single slice or many slice. This is the standard one, the default one. And for the automatic one, we just click this button. And in the QCT, will detect the material, the object. This is 4 object here. And then the IndoQCT will measure the MTF from the 4 material, and then the IndoQCT will show you this one. This one is the TTF10 from different CNR, contrast to noise ratio, because we have 4 material, and so we have 4 contrast to noise ratio. This is the dependency between the contrast to noise ratio and the TTF10. And it is important to note that if we have the TTF like this, we can export to the Excel. For example, I can export and we can analyze further by using the Microsoft Excel. In this example, I will export this curve by using click the button export, and I will save in the E, and in this location, the example, for example, example of TTF, and then save. So our data is already export to the Excel file, and then we can open our Excel file in the D, and the name of file is example. Mana? Mana? Ini this one is example TTF. Okay. This is our data, and of course you can analyze and you can compare. You can compare with another. You can compare with another, maybe another protocol. Okay, you can also make your curve in this Excel. Okay, and then insert, and then this one. Sorry, TTF spatial resolution. Manual. Yeah. Okay. Yeah, like this. I think you are familiar with the Microsoft Excel. So you can export to the Excel and you can analyze further. Okay, and for the Z-axis MTF, the first one you should make the to make reformatting in the sagittal or coronal plane, and after that you save your image, and after that you open again that images, and then you can measure the MTF in the Z-axis. Okay, I think it is enough for me. Maybe there are many questions to Dr. Nurdiana. Thank you very much.
Okay, thank you very much, Dr. Khairul Anam, and also Dr. Nurdiana for a very fascinating presentation and the practice. So we come to the discussion session. We have some question here in the chat column in the Zoom meeting. The first one, I think this first question is already answered by Dr. Nurdiana, but maybe Dr. Nurdiana have some enhancement regarding to this topic. Is visual observation considered as objective or subjective? Please, Dr. Nurdiana.
Okay, thank you, Suchi, and thank you, Ashraf, for the question. So usually visual observation is subjective because it depends on the observer. Okay, for objective, it's actually it's no variation. It's based on the one specific parameters. It's subjective because sometimes in spatial resolution, although we can see the line pair, but it actually varies among observers. Some observers can see, but some observers cannot see. So it depends, and also it also depends on the monitor that you use to visualize your image. That's why in CT, in clinical practice, you also have um, to test your monitor that you use to visualize. You have a specific test for the monitor also. So it is more to subjective. To answer your question, it is subjective.
Okay, thank you for the answer, Dr. Nordiana. And then the second question is from Muhammad Yasin. What is the reason that screen film system have higher spatial resolution compared to the CT?
Okay, to answer this question, okay, screen film, it depends on the properties of the films, okay, because we know in conventional films, the properties is actually depends on the, because we know it has silver halide crystal, which is more smaller compared to CT. Now, we use detector element. Okay, if you have more detectors in your multi-detectors, okay, so the spatial resolution will be higher, but it's still not as smaller as the crystal of the films. So that's why screen film is considered higher spatial resolution, but because it is a projection image, so it's still not superior compared to CT. Okay, so actually because it depends on the film properties that has smaller crystal compared to detector element, which is limited. Yeah.
Okay, thank you. And then we move to the next question, Dr. Nurdiana. It is from Mohammed, Mr. Mohammed. I am not doing QC or QA, but can I simply use any phantom or patient images and find the spatial resolution in IndoQCT?
Okay. For specific spatial resolution, you actually can use any phantom that has the features or the test pattern for spatial resolution. Okay. You can also use for each MTF, you can use water phantom because it has the features. Okay, but from my experience, I never explore using patient image. So I'm not really sure. Maybe this part I can ask Dr. Anam
Yeah,
because I never
thank you.
test out. Yeah.
Yeah. Actually, we will explain how to measure the image quality directly to the patient in the, I think that in the last session of this summer course. Actually, the IndoQCT can also measure the image quality from the patient, for example, from the MTF, but still many limitation. And now many researchers from around the world also try to measure the image quality, especially MTF directly from the patient. And I see latest publication published in the GSCMP, they also measure the image quality directly from the patient, and they also using in the QCT.
Oh.
Yeah.
Okay, is that enough, Dr. Anam?
Yeah, enough. Yeah.
Okay, we move to the next question from Mr. Wahyu Hutomo. Mr. Anam recommended that we use high-dose scanning parameter because the spatial resolution is prone to noise fluctuation. So, what is recommended scanning techniques factor, SKV, MES, or etc. for this measurement? Maybe from Dr. Nordiana first.
Okay. So for my routine QA, usually I use the recommended parameters by the manufacturer. Okay, it's a standard dose phantom. Sorry, standard dose city protocol. So I never use high dose and I never test. Maybe this one can ask Dr. Anam because usually the recommended scan protocol that I use is based on the manufacturer recommendation.
Yeah.
Any enhancement from Dr. Anna maybe?
Yeah, thank you. If you measure the spatial resolution using the point MTF, it is prone to the noise.
Mm.
Yeah, so it is recommended to use the high dose. But it is should be carefully performed because if you use the high dose, it is in large low. So I recommend not to use the point MTF because it is prone to the noise. I recommend to use the edge MTF. I think it is resistant to the noise.
Okay. Okay, thank you, Dr. Anam, for the very clear answer. And here the feedback from Mr. Muhammad Yasin. He will try to ask question through the email, inshallah. Okay. We still have 5 minutes left, maybe, for all the participants. If you still want to ask a question to both of Dr. Nordiana or Dr. Anam, you can raise your hand and we can discuss. If there are no questions, maybe I will ask one question to Dr. Nordiana. Dr. Nordiana, in the context of measuring the spatial resolution, how do the point MTF and also the edge MTF differ in terms of their potential sources of error in obviously in the medical imaging systems?
Okay, as mentioned by Dr. Anam just now, for PSF, usually it depends on the noise. Okay, so it's a fluctuation in the situation that affect the PSF measurement. For each, you should actually have object with a sharp edge, so it will give you a better edge MTF. That's the factors that affecting the PSF and age. Maybe Dr. Anam can have other comment.
Yeah. I think that using the point and also using the S, they have their own limitation. Yeah, using the PSF, it is very prone to the noise, and by using the ESF, because we need additional because we should the differentiation from the edge to the point spread function. So this is a so in the some paper said that it is also prone to the error. So but now if we using the TTF, the TTF is on the ESF. So I think using the ESF is better, and now many mathematical function to make the ESF is better. Okay.
Okay, thank you very much for the answer, Dr. Anam and also Dr. Nordiana. Okay, maybe we can wrap up this session. And Dr. Nordiana, would you like to give a closing statement for your session this afternoon?
Okay, first of all, I would like to thank Dr. Anam for helping me and assisting me with the demonstration. Okay, so from my experience, I think IndoQCT is one of the best tools that offer you an automated measurement, because using our manual measurement is sometimes limited. And then if you are at the busy center, you actually didn't have time to analyze. So automated measurement is the best assistant for you. Okay, for example, at my center, we usually usually perform monthly QE test for our PT system. So IndoQCT really helpful in my routine practice.
Okay, thank you very much, Dr. Nordiana, for very insightful lecture, and also Dr. Anam for give us a sharing knowledge for this afternoon session. We come to the end of this afternoon session, and we will continue in the next Tuesday, because this Monday is there is a no, there's no lecture in this Monday, but we will continue in the Tuesday with another interesting topic. So we would like to remind to everyone to stay tuned in this summer course and following our schedule until the last day. Okay. Thank you very much once again for Dr. Nordiana for joining us this day and also Dr. Khairul Anam and everyone. We can end up this summer course for today. Thank you and wassalamualaikum warahmatullahi wabarakatuh. See you at next week.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Nadiana, and thank you
Thank you,
for all
Doctor. Happy
participating.
weekend, everyone.
Okay, okay. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.